right, thanks everybody for coming. I'm glad to be here. Always glad to be talking about Stan. However, when I do talk about Stan, I have to get this out of the way that as a Columbia University employee, and Columbia gets a lot of grants, I also do some stuff on the side, and according to Columbia University policy, any such employee who meets a variety of criteria, such as expecting to earn more than $5,000 per year from a private company, is required to disclose these facts in presentations. So if you want to bribe me to say good things about your software, you have to pay in euros. Otherwise, I can't. So I want to make 4 key points. First is if you're doing numerical differentiation, you should have stopped about 5 years ago. It's not accurate in some cases when automatic differentiation, which is implemented in Stan, is. Second point, optimization is worse than sampling. At best, you're going to find the behavior of your function at the optimum. You can assume it's normal all the way down, but you have no real way of verifying that, whereas MCMC will give you the behavior of the entire function in proportion to its probability. Third key point, GIBs, especially Metropolis Hastings sampling, are worse than no U-turn for differentiable posterior distributions usually, or GIBs can be about the same. There's special cases in which you can prove that GIBs is mixing fast, but in those cases, Stan tends to mix approximately as fast. And fourth, it's easy to build your own R package that utilizes Stan's implementation of MCMC, and that's what I mostly want to focus on, how to do that, but I'll also try to talk about why. So what is Stan? We've been around 5-6 years, but apparently not everyone in the world has heard about us yet. It's a new computer language. It's a much simpler language than R, but for expressing statistical models, and its primary advantage is that it's easy to translate into C++. So you as the person can write high-level Stan syntax. It can be translated to pretty low-level C++, and the compiler can do all kinds of optimizations, including linking to the Stan math matrix and scalar library, which supports automatic differentiation, which I'll talk about more in a minute, with the ability to do these derivatives automatically, that is to say without any human intervention to speak of. You can implement new or old algorithms based on gradients for statistical inference. I'm particularly proud of the new ones for Bayesian inference, but you can do old stuff as well. It includes interfaces to Stan from R, other languages such as Python, Julia, etc. We have a bunch of post-estimation functions in various R packages to help you understand the output. And most importantly, Stan now includes a large number of users and a lot of developers too, who are going to be more than happy to help you out. So who is using RStan? It's being used throughout academia, increasingly so with business and government. There's, at last count, 37 packages which depend on RStan in some way. My links to the downloads didn't come through here, but we're averaging about 10,000 a month for RStan and a few thousand a month for these other ones. Profit was a package using Stan put together by the guys at Facebook, and they released it to the public. It's been exceedingly popular for doing some time series forecasting. There's all sorts of applications. If you heard Marco's presentation yesterday from Pinnacle, he basically said, well, their business model is to produce good statistical modeling, and they use Stan to do it. Prescription drug companies have been really excited about Stan because you can have your conditional mean function be the solution to an ordinary differential equation. And so there's tremendous flexibility. It's really intended for people who really want to estimate good models, especially if you have a lot of money on that. So that did not, my internet is not working. Okay, so translate the LaTeX in your head. But remember this part, numerical differentiation is not a good idea. Yves was talking about this yesterday, that there's forgetting all the things that we thought we used to know about numerical computation. And one of the things we used to know was never subtract 2 numbers that are approximately equal to each other, which is what numerical differentiation, as you can see here, does by construction, by just perturbing one element of the function, seeing how much it changes, and dividing by a small number. That's called cancellation, and it may not give you a good approximation to your function. And moreover, you don't know whether the approximation to that derivative is good or not, just from the output. Automatic differentiation doesn't suffer from cancellation. It's about as accurate as your function is in the first place. And automatic differentiation basically goes like this. You have a library of functions. They all know their own derivatives. And you can write C++ code that instructs the C++ compiler. It teaches it calculus over the course of like 30 seconds. And it knows how to do the chain rule, and so it can accumulate up all these derivatives and give you the derivative of a complicated function with respect to any parameter that you want. There's a variety of approaches, most of which use C++. Stan is arguably best for the workloads it was intended to use for, which is statistical inference, particularly Bayesian inference, and there's a link in the good version of the slides to a paper substantiating that. So what if you want to minimize this function using C++. Is Dirk in the house? No? Anyway, Stan works well because of all the effort that Dirk has put into making C++ work well in R. So you can just have these 3 lines which bring in the linking to the packages you need, BH, RCPB, eigen, and Stan headers. You have a couple headers including the Stan math. That's going to pull in everything. You could be more precise. With that, anyway, the function we want to minimize is the square difference between 2 vectors x and a, treated as a function of x. So you can write your C++ function in terms of doubles using the .self function, which is the dot product of a vector with itself. Write the same function using the Stan math var type. This is going to be used, this is not exported, but it's going to be used to calculate the gradient. And the gradient function I have kind of compacted here because I was running out of space. But basically, it takes in x and a in doubles. It coerces x into a vector of Stan math var types, allocates some storage, pushes some things back, and then calls the function f, the middle version here, in terms of Stan math vars. That will evaluate the function and give you the ability to evaluate the grad method, which will put the derivatives with respect to x in this standard vector of doubles called grad, and that can be returned to R. And so if you call this function with optimum, you'll recover the correct minimum, which is x equal to a. So relatively easy C++. You can use that using Stan, take advantage of automatic differentiation. Not everybody wants to write C++, so you can do the same thing in a much more user-friendly, in my opinion, language. Stan, we have like 5 lines here, an integer saying what length of the vector you want to consider, constant vector a, which is what you're trying to target here. You have an unknown vector of length k called x that we want to find the solution for, and our objective function is just the square difference between x and a accumulated. Stan, because it's oriented toward Bayesian computing, unlike minimization, so you have to multiply it by -1. If you want to do optimization, there's an optimization routine. It does LBFGS by default in Stan. Knitter took the top part here, created a Stan model object called SM. So I want to take the opportunity to thank the RStudio guys for integrating Stan file types and syntax highlighting and whatever into RStudio. I'm not sure how many of them made it today, but we really appreciate it. Anyway, if you take a to be the vector 1, 2, 3, minimize this function, you find that x is equal to 1, 2, 3. And obviously, you can do more complicated optimization problems than this, but when you do so, you don't have to worry about the derivatives. But you don't actually want to do that. Generally speaking, if you want to build your R package, Paul's going to talk next about BRMS, which is the exception. You don't want to replicate the Stan user experience that someone does when they're just typing at the keyboard. One, it requires your users to have a C++ toolchain. Half of them won't. It requires users to wait like 30 seconds for the thing to compile and then take less than 1 second to minimize. And for doing packages, you can't do 5-second examples or 2 minutes of unit tests if you're taking 30, 45 seconds to compile the thing at runtime. And there's ways around that. You may have heard Stata 15 came out recently, and you can put the Bayes keyword in front of like any Stata command. and it will do Bayesian estimation, so to speak, using Metropolis and Gibbs sampling. And long-term goal for RStan is to make the same facility available for R, but to do it correctly. And to see where things can go wrong, imagine, again, with the LaTeX that you're trying to draw from a 250-dimensional multivariate normal that's pretty highly correlated. And you can do 1 million draws of random walk Metropolis. You can do 1 million random draws of Gibbs. You can thin every 1,000, and you get the two plots on the left, which when compared to 1,000 draws from RStan, unthinned, and 1,000 independent draws from the multivariate normal, the two on the right, which your eyes can't even distinguish from each other, but definitely can distinguish from the two on the left, that they never reach the tails of the distribution because these Markov chains don't mix fast enough. You really have to mix quickly in order to have the intuition that you try to carry over from, like, what if we could do independent samples. The samples from nuts, if you do it well, will be almost independent, not completely independent, but pretty close. So users can use RStan without personally knowing the RStan language if you have an R package that provides a wrapper. RStan ARM was the first to go down this route, and it was hard to do originally because I was the one doing it originally, but I wrote tools to make it easier for everyone else to do. Anyway, RStan ARM emulates the syntax and carries over the likelihood function for a bunch of popular functions that are already in R, adds some arguments for priors, uses RStan to draw from the posterior distribution, and other people that are not me have followed the same path, as you can see at the bottom here, providing other packages that could other RStan models that are already precompiled and ready to go. So here's one slide that actually did come out correctly. Since we're in Belgium, I thought we had to do a chocolate example. It also reminds me to thank all the people who put this together. We really appreciate it. Anyway, the cake data frame comes from LME4. Change the scaling a little bit, put it in this function in RStan ARM called stan_gam4, which the first part of the formula has a spline additive term. This is parsed by MGCV. The random component of it is parsed by LME4, so you can estimate models with hierarchical structure, nonlinear functions, and in this case, it turns out to be linear in the log scale. So you can get the whole posterior distribution of that. So what if you wanted to do your own model? Here's an example of regression with student t errors. By the way, there's no real reason to expect maximum likelihood to do very well in finite samples for something like this where you're estimating the degrees of freedom because there's no sufficient statistics for that. So you can write a RStan program, looks like this. There's a likelihood, there's a prior on the degrees of freedom. This target accumulates, and that's the kernel of your posterior distribution that RStan is going to draw from. So if you call that file treg.stan, there's a function in the RStan tools package called RStan_package_skeleton that works like the regular package skeleton and comes in R, but enables you to use RStan. It makes a bunch of files here. The cleanup functions are ironically named because they actually create files. They work with the make CPP function in the file at the bottom there to create the C++ version of your RStan files. You can use the inst directory to include common functions that you want to use across. And then there's some R functions, particularly the ZZZ, that loads the modules at runtime and enables you to do it. So the last thing you need in order to expose this treg function or treg package to users is to write a R wrapper that takes formula, data, etc., any priors that you want to do, parses the thing, makes a list of RStan data to pass to RStan, and the key line is this. You have a precompiled model here that's a named list that you can just reference, call the sampling function, maybe process the output a little bit more, and return. So if you want more information, read the read and delete me file. There's also a vignette in the RStan tools package that will help you connect it with the post-estimation function. So finally, where to start or get more help, look at RStan ARM. It's pretty complicated, but it's pretty comprehensive. I already mentioned the vignette for RStan tools that will tell you about the package skeleton. I have 700 pages of documentation that you can read overnight or whatever. We have a whole repo of Stan programs that you can take as inspiration for your examples. We have a mailing list where you can post questions, and usually me, if it's about R, will answer. We also have a conference coming up in California, January 2018, and we'd love to see you present your package using Stan there. Thank you.